Hi everyone, I am Balaji. In this LinkedIn post, I'll explain my uh, recent experimentation and what I have found. I tried to visually represent how artificial neural networks and convolutional neural networks work under the hood. The inspiration in trying to interpret these deep learning models stemmed from my previous experience. Once I was working on a project in which I need to make a API call to OpenAI, and in that API call, I used to give it a raw string, and I expected a structured JSON response. I used to always tell in the inference part that this is the uh, example JSON structure. Please follow it. Give it to me. But time and again, it used to fail. Sometimes it used to work. Sometimes it used to fail. Some of the issues were like giving a trailing comma, which is invalid in JSON, and the other one is sometimes you used to give string instead of float values. That is incorrect, and the many other issues and also inconsistencies. Sometimes when you ask ChatGPT, it will be like, here you go, here is a JSON response, and then it will create a JSON. So uh, all these issues I was not able to resolve myself. I was like, what's happening? Why isn't this working um, consistently? There is lack of consistency. So I want to interpret models. So this post is about explaining how actually ANNs learn. We might so this post is about trying to interpret ANN and CNN. So deep learning is based on universal approximation theorem. So it states that with any sufficient complex neural network, you can approximate any continuous function. So I want to see it. I want to visualize how our models are learning. So I took very simple three easy functions: line equation, parabola, and another continuous function which is sine wave. Oh, so now let's see how they perform. Starting, I took a very simple single layer 4 neuron deep learning model and trained it on line data. This is how the line data looked like. The line equation is y equal to x plus 5, and this video shows how, if you look in the starting, I used ReLU's activation function, and if you see it, initially it thought this is the approximate function, the approximate function, but slowly after learning, after a couple of epochs, it started correctly predicting the line equation. So later I want to see how the weights and biases look like. So I made a small render. I printed all the weights, all the biases and the visualization, and this is how it looked like. Here, the only small change is that I used Gelu instead of Relu. I just wanted to try Gelu because in the attention is all you need paper, Gelu was used, so I thought of just trying it. That's why it's a little bit different. If you observe closely, our data is a straight line, but this is not a straight line. The approximation theorem says that we can approximate a function, but it may or may not be exactly like the function. It might not be a straight line. That's why after even after 400 epochs, it is not a straight line, but it's almost like a straight line. Here, these red dots indicate negative values, blue dots indicate positive values. The larger the dot, larger the value. Smaller the dot, smaller the value. So this equation is approximately equal to mx plus c, x plus 5 equation. So later I want to try on the parabola data. I wondered ki ReLU will clip all the negative values to 0. So whether ReLU will work or not, I don't know. So I want to try. So I tried on ReLU. Initially, I thought it's not learning until like 100 epochs also it was nothing promising, but later it started looking something in a V shape. Of course, it's not a parabola, but it looks something promising. So I trained it for more number of epochs, and it almost approximated a parabola, which is surprising good. As a single hidden layer with four neurons, it was able to approximate it. Next, the more complex one is sine wave. So sine wave is a periodic function. So I thought this would be a great challenge, and I trained the same sine data on a single hidden layer with four neurons using ReLU and GALU. All of them failed; they did not work. Later, I thought, okay, ReLU might not be working well. I used sine activation function, um, but even sine activation function failed. Later, it also failed to work. But later, I increase. So I increase the complexity of model, uh, and this is what happened. I used 1,000 points, and the batch size is 1,000. So it was not learning, even though the loss values are very close to zero. Why is this happening? Since sine wave is a periodic function, uh, the values are complementary. The loss values in the batch are complementary. That's why 500, whatever the loss is created by 500 training examples in the dataset, another 500 is cancelling out them. That's why the loss is low, but still the model is not learning. So what I did now, I just changed the batch size, and voila, it started working. It took some epochs, but yeah, it started to form a sine wave. Nice. After 200 epochs, there are some, it looks something like a sine wave. See, great. Later, I did the same for 50 epochs, sorry, batches of 50, 20. The smaller the batch size, the faster the convergence was. Initially, it took about 400 epochs to become a good sine wave, right? When you use a batch size of 20, it's much, much faster. Um, Later, I wanted to try whether the ReLU or the variance of ReLU can approximate it. Function, but I was curious whether sine, instead of sine, if we use something like a ReLU, can it do it or not? So I tried it, and guess what? It did. It worked. Even ReLU was able to do it, and it did it much faster. Yeah. And also, I want to try whether sine activation function, a complex neural network with sine activation function, can approximate a line. Line is linear, sine is periodical. So I want to try, and let's see what's the result. Yeah, it did. It worked actually. And it's very close to line as well. Even when I use ReLU, there is a small bump like this at a place. But when I use sine activation function, but this is a much more complex neural network. It has a lot of layers with 64 neurons in each of the layer. So yeah, it still worked. Yeah, especially it has two layers with 64 neurons in each. So it was able to approximate very well. Now that we understood that ANN is trying to learn what is the um, relationship between the input values. Like what is the relationship between the input and output values? Here we are using single input X and the output is Y. But we can also scale it using multiple input features, and it will give one single output feature. It will work really well. It will figure out what is the relationship between all the input features and how it is related to the output feature. Sorry, target variable. In CNN interpretation, so in CNN interpretation, to understand the feature extraction process, to see how CNN performs transformations, image transformations, convolution operations on the input image, I took a red fill circle and the target variable is a outline circle. I want our CNN to figure out what are the filters that needs to be applied on the input image to get a target image. So basically this transformation can be done using two consecutive filters. One is an edge filter, the other one is a dilation filter. This will result in this image, but I want the convolution neural network to figure it out on itself. So I trained it, and this is how it looked for each epoch. So after 100 epochs, we'll look, yeah, it's here. Here 150 epoch, it successfully transformed into outline circle. This is how in one layer how an image is being transformed into another image. It's called feature map into another feature map. So now let's get to the final experimentation. This is the most fun one. So in the previous, so this is the fun experiment. So in this experiment, I took a convolution neural network. It has 6 layers. It has 6 layers, and I have trained that model on 4 images. First, images are these 4 images: square, circle, triangle, and a cross. I trained that model so that whenever a square is sent to the model, it will say it's a 0. When its circle is sent, it says 1, triangle for 2, and cross for 3. So this is a classic classification problem. And my goal is to try to interpret what's happening to the image in the intermediate layers. What is happening? Can we as humans, can we see it visually and say this image belongs to square and this image belongs to circle, this image belongs to triangle? Can we do it? So I trained the model. So initially I trained the model for 4 layers and it performed excellently well. It performed well, but later I wanted to make it into 6 layers, because when we perform convolution operation, the size of the feature map will start decreasing. So I used or trained the model. The model has 6 layers. So this is the first layer. These are the outputs from first layer. These are the outputs from second layer. These are the outputs from third layer, fourth layer, fifth layer, and sixth layer. So as we progress from first layer to sixth layer, the number of pixels, they seem to be increasing. Here it is this big. The thing is, it's not the pixels which are increasing, it is actually the image, it's reducing. The size of the image is reducing. When I'm plotting them, it's looking like the pixel size is increasing. In reality, the image size, the feature map, usually when we send a image into a convolution layer, the output image is called a feature map. The transformed image is called a feature map. So since I have used 4 convolution filters for each layer, 4 kind of transformations is performed on the image. So this filter is detecting a line on the bottom side. This filter is trying to detect a line on the right and bottom. This is trying to detect a line on the right side. This is trying to detect the top. Along with that, the middle one is gray. So it is trying to come up with some other different primary feature which is useful for classification. So as we progress into the layers till the third even till the fourth, maybe not the fourth, till the. So as humans, we can understand whether this belongs to a square, or this belongs to a circle, this belongs to a triangle, or this belongs to a cross. But how do machines understand? So this feature map is again uh, flattened and sent into a fully connected layer, where ANN will predict which class it belongs to. We already know that ANN is good at classifying. These values, these pixel values, are basically numbers. Numbers we can pass as input features to a fully connected ANN neural network, and that will try to find what is the relationship between the input features and try to predict it. So let's look at this sixth layer. In the sixth layer, the first image and third image are completely black. Here in circle also, the first and third image are completely black. In the triangle, the first and third are black. In the fourth image, the cross, first and third are completely black. So it means black means 0. So when the value is 0, it is contributing, it is not contributing to the classification. So we can eliminate these two feature maps, and we can consider only the second and fourth feature map. And we can, as humans, with our eyes, we can also say this certain feature map belongs to square. So I have uh, cropped all the feature maps into a single frame. So here we can see, for square, the feature map, the second feature map started with a black, and below it there is a white. If you look at cross, the feature map, the second feature map, it started with white, and below that it's a black. So as humans, with our eyes, we can distinguish between the feature maps between each image. But we need not do it. This is only for interpretation purpose. Basically, ANN will be able to classify what is the relationship between those values. What is the relationship between the pixel values in the feature map, and it will do the classification. So
So
uh, I
I
hope
hope
someone
someone has
has I
I
hope
hope
someone
someone
has
has
found
found
it
it
insightful
insightful
and
and
learned
learned
something.
something.
If
If
you
you
enjoyed,
enjoyed,
if
if
you
you
learned
learned
something
something
valuable
valuable
from
from
this,
this,
if
if
you
you
like
like
this,
this,
please
please
don't
don't
forget
forget
to
to
like,
like,
comment,
comment,
and
and
share.
share.
Bye bye.
Bye.